I like to think about what it was like when I was a small child and I first started to wonder about things. Maybe the most profound question that I knew how to ask was, what is all of this? You know, the planet and everything beyond the planet. And if I was being a little more detailed, I'd ask, and how does it get to be that way? Where did the universe come from? Where did our planet come from? Where did human beings come from? All of that was in the realm of poetry, of philosophy, of theology for millennia, and the 20th century began to change all of that. All of a sudden, we actually began to ask questions of the universe itself. And that's why talking about and asking the question of where did the entire universe come from is no longer a question for poets and theologians and philosophers. This is a question for scientists, and we have some amazing scientific answers to this question that have totally, in many ways, defied even the wildest of our expectations. Pause for dramatic effect. I'm Ethan Siegel, theoretical astrophysicist and science communicator, author of the James Webb Space Telescope book, Infinite Cosmos, and writer of the science blog, Starts With a Bang. Let's get into some weeds. So we have this idea of where our universe came from that most people have heard of, called the Big Bang. And the way we came upon this idea was we weren't actually looking for the beginning of the universe. We were looking at these faint, fuzzy objects that appeared through telescopes that looked like little spirals in the sky. And we were wondering, what are these things? And then some critical observations came in. It started in 1923. This astronomer named Edwin Hubble had access to what was then the largest, newest, and most powerful telescope in history. And he was looking at the largest of these spirals that we see in the night sky, which today we know as the Andromeda Galaxy. And Hubble was saying, hey, I can see that there are these bright flares that go off. Something appears to brighten, and then it appears to fade away. Maybe these things that we see are novae, or, you know, the plural of nova, happening in Andromeda. And he said, well, goodness, a nova can't repeat itself in just a day or two. Novae take years, decades, centuries, or more to recharge. So if this isn't a nova, what could it be? And he realized, oh, this is a variable star. And these classes of stars that do this brightening and faintening over time had already been studied for decades by a woman named Henrietta Leavitt, who said, oh, these are what we call Cepheid variable stars. And there's a relationship between how quickly they brighten and fainten and how intrinsically bright they are. Just from how bright you see it, you can know how far away it is. And that was what Hubble did, is he said, well, if I observe this star over time, I can figure out how distant it has to be. And it was by doing that that Edwin Hubble first said, oh my goodness, this nebula in Andromeda, it can't be within the Milky Way, because it's not light years away or hundreds of light years away. It's something more like 1 million light years away. Today we know it's more like 2.5 million, what we would now call extragalactic objects. So Hubble took his same telescope and with his assistant Milton Humason went out, and what he found was that in fact the Andromeda galaxy was one of the closest ones to us, and that he was finding galaxies that were over 100 million light years away. And he was able to say, well, now I also have these observations from this older guy, Vesto Slipher, who was measuring how fast these objects appear to be moving away. Light, just like sound, is a wave. If a light source like a galaxy is moving towards us, the light that it makes is going to have a wavelength, or what we call in astronomy, blue-shifted. But the opposite is also true. If the object is moving away from you, the wavelength lengthens and the light becomes red-shifted. Hubble put this together in the late 1920s and early 1930s. But the first one to do it was in 1927, a Belgian Catholic priest named Georges Lemaitre. And he said, what does it mean that the farther away a galaxy is, the more its light looks redshifted? Well, the way I like to think about it is to think about baking. Have you ever had a ball of dough? And I don't want you to imagine plain, boring bread dough. Let's make it a little exciting and let's put some raisins in there. So what happens? As the dough starts to leaven, the raisins get carried by the dough, so that from the perspective of any raisin within the dough, it looks like the other raisins are moving away from it. In this analogy of the expanding universe, the raisins are galaxies, and the dough is this fabric of space itself that comes up in Einstein's general theory of relativity. In general relativity, space and time are woven together into a fabric. But this fabric is not constant. This fabric can evolve with time. And it wasn't actually Einstein who figured out how the fabric evolves. It was a Soviet scientist from 1922 named Alexander Friedman. Friedman said that the universe is going to either expand or contract. Otherwise, it won't be stable. So Lemaitre was the first to put all of this together. Einstein's equations, Friedman's solutions, Vesto Slipher's redshift observations, and Hubble and Humasson's distance observations. He put them all together and said, oh my goodness, look what this means. The universe is expanding. And he said, well, hang on. If the universe today is expanding, then in the past it was smaller and everything was closer together and it was more dense. All of space and time and all of the matter and energy within the universe was once compressed into this tiny, indivisible point. And he called this point the cosmic egg. Something that today we might call a singularity. And this is where the big idea of the Big Bang first came from. All of these cornerstones of the Big Bang singularity are now in place, but people are still asking questions. One theory is before the Big Bang was a period of cosmic inflation. I want to start by going back to Alexander Friedman. Alexander Friedman was the first one to say, hey, if you have a universe that's uniformly filled with any type of matter or energy, it's going to either expand or contract. So for normal matter, what is its energy density? It is how many massive particles you have in a given region of space. As your universe gets bigger in all three dimensions, the density is gonna go down. It's gonna dilute as the volume of the universe increases. What about if your universe is made of radiation? A universe with radiation in it is going to dilute more rapidly. Its energy density is going to drop faster, and that means its expansion rate is going to drop at a different rate. But what if the universe wasn't filled with matter or radiation. Einstein didn't even know it, but he first put forth this possibility way back with the general theory of relativity. This is what he called a cosmological constant. And in this case, we get a universe that expands not just rapidly, like a matter or radiation-filled universe will do early on and then decrease. It's going to expand at this rapid rate, and it's going to keep doubling relentlessly. So the idea of cosmic inflation, thought up by Alan Guth and then since worked on by many, many others, was that there was a phase that preceded our universe being filled with matter and radiation, where instead it was filled with a form of energy that was intrinsic to space itself. And while it was in that phase, space got stretched to be enormous in a minuscule, tiny amount of time. So we've got these two ideas now that are not compatible with each other. Either we had a singular hot Big Bang that gave rise to the hot, dense, rapidly expanding state, or we had cosmic inflation, this state where space has energy to it, becomes large, becomes uniform, spatially flat, and then inflation came to an end and gave rise to this hot, dense, rapidly expanding state. I like to think about it the way I think about a ball atop of a plateau that ends in a valley. As the ball stays on the plateau, you get inflation. But as the ball rolls off of the plateau into the valley, it loses energy, and all of that energy gets converted into matter and radiation. That's how we go from inflation, which is relentless and rapidly expanding, into the hot Big Bang. So how does inflation make predictions that differ from a Big Bang singularity? Well, if inflation only gives you a certain amount of energy inherent to space, and then it decays into matter and radiation, that's a different prediction right there. Because first off, this tells you for the universe that starts with a singularity, we're not going to have a maximum temperature or a maximum energy that it gets up to. Whereas with inflation, no. We were at the top of a plateau and we rolled down, and there's a limit to how hot the universe can get. So if that's the case, there should be a difference that we see imprinted in all things of the cosmic microwave background in that leftover primeval fireball from the Big Bang. Now, there's a second thing that comes about from inflation that is remarkable, and that is due to the fact that right now we've been thinking about inflation as being what we call a classical field. We've been picturing it like it's a ball on top of a hill. But it's more than that. We live in a quantum universe, and inflation should be a quantum field. And one thing that quantum fields do is fluctuate. So think about what happens if you have a little fluctuation in space and your universe is inflating. This fluctuation gets stretched, and then the universe keeps inflating, so it gets bigger and bigger and bigger. While on tiny quantum scales, new fluctuations get created. So I should have a set of quantum fluctuations that exist all throughout the universe. And they should be there on all scales. Now, the beautiful thing about this is when inflation comes to an end, when the ball rolls down into the valley to convert things to matter and radiation, that means those smallest scales, they get stretched just a little bit less than the larger scales. So inflation gives us this specific prediction that when we look at the fluctuations imprinted on the universe, they should be almost perfectly uniform on all scales, except on smaller scales, we call this an almost perfectly scale invariant spectrum. And that's something we should be able to go out and look for. So one test is, do we see a maximum temperature imprinted in the cosmic microwave background? Second test is, do we see an almost perfectly scale invariant spectrum, but with smaller fluctuations on small scale slightly than on large scale? A third prediction that should be made is, if we have inflation going on for a long enough duration of time, it shouldn't just be stretching quantum fluctuations to a maximum scale of the observable universe. It should be stretching them continuously to all scales, including scales that are larger than the universe we can see, what we would call super horizon fluctuations. Those should be imprinted in the leftover glow from the Big Bang as well, whereas in a universe without inflation, you don't get those. So right there is 3 observable tests. We've now been able to go out and test those predictions of inflation against the singular Big Bang without inflation. And what do we find? Well, we find that there is a maximum temperature that the universe got up to, and it's a high temperature. It could be as high as about 10 to the 16 giga electron volts. Wow, a lot of energy. Guess what? That's about a factor of 1,000 below the Planck energy. There's a limit to how hot the universe got, and it wasn't arbitrarily high. We can look at the fluctuations we see, and guess what? They are almost perfectly scale invariant, but the fluctuations on the largest cosmic scales are about 3% larger than the ones on smaller cosmic scales, consistent with what inflation tells you. We can look for, do we see evidence for the existence of super horizon fluctuations? And the answer is yes. So all of these, consistent with inflation, disagree with the singular hot Big Bang. You might ask, what's left? What's left for inflation to do? And so far it's passed 100% of those tests. The big thing we'd like to know is, I drew you a potential where I said, imagine a plateau and we fall into a hill and we oscillate in that valley at the bottom of the hill. We want to know, is that the right model for inflation? There are alternatives. What does the shape of that potential look like? There are 2 big frontiers that we're trying to push to gain answers to those questions today. One is to look at the spatial curvature. So far, we've only measured it down to about the 1% level, or the 1 part in 100 level. And it is spatially flat down to that. But if we can get a few orders of magnitude more precise, we'll be able to see what is the precision to which our universe is flat. Is it consistent with what inflation predicts, or does it not match? And finally, there's another type of fluctuation that should exist. There should be gravitational wave fluctuations imprinted by inflation on the universe. And there is an effort to look for these being conducted at the South Pole. So the more precisely we look for this signal, the better chance we have of not only finding these leftover signals, but of learning exactly what the properties of our cosmic origins, of cosmic inflation, were at those critical, very first moments that led up to the hot Big Bang. Since time immemorial, no creature came along on Earth that understood where we were in the universe, where we came from, and how we got to be here. All of this is new, like within many of our lifetimes new. We now know the universe began not from a Big Bang singularity, but from a state that was rapidly and relentlessly inflating, where space was empty, filled only with the energy that was inherent to space itself. That inflationary state came to an end. That gave rise to the structure that came about in all the time since. Stars, galaxies, planets, and human beings. Here we are today, 13.8 billion years later, and we know our cosmic origins up until that moment. But big questions about the specifics of what inflation was and how and whether inflation began as well as what came before it are still mysteries waiting to be solved.
Okay, tell us about your kilt really quick, Ethan.
Oh my goodness. About 6 or 7 years ago, I had been wearing kilts for close to a decade, and I met an artist who specialized in fabric painting and loved doing space work. What she brought me back was gorgeous, and I was very pleased with it. And in the time since, I have had 3 additional kilts that I commissioned by her, and this is the most recent one featuring the James Webb Space Telescope, NASA's newest flagship observatory for astronomy and astrophysics.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.